Hi everyone, I am Yiren Zhang from Shanghai AI Lab. I am here to present our new work named as Accelerating Toeplitz Neural Network with Constant Time Inference Complexity. The source code of this work has been released at the GitHub link. Before entering the main body of our work, let us recap what is Toeplitz Neural Network. We abbreviate it as TNN. TNN is a new sequence model architecture that belongs to long convas. Here, an attention with relative positional encoding can be written as the equation here. The relative information is added to attention as a bias. However, in TNN, the attention operation is changed to Toeplitz matrix operation. In short, the QK multiplication in attention operation is discarded and the relative positional matrix remains. We use a small MLP to generate relative positional coefficients. Although the TNN is faster than transformer, the inference computational complexity is OND log n, which is slower than linear attention and RNNs. State space model is also a new sequence modeling method that uses state space equations to model sequences. The benefit of using SSM is that the inference computational complexity of SSM is OHD, where H is the hidden dimension. However, the SSM is often weak in language modeling. Since TNN has better language modeling capability and SSM has a faster inference speed, can we convert a trained TNN model to SSM model to enjoy the best of both worlds? The answer is yes. Let us consider the token mixing operation of TNN and SSM. Let us set T bar equal to CAB. We have Y equal to the sum of T bar times X. Recap that CAB is equal to the sum of CKB k lambda k and set C equal to 1, we have the fourth equation. By comparing the first and the fourth equation, the problem is equivalent to find matrices A and lambda such that the fifth equation is satisfied. To solve this equation, one naive solution will be using a gradient descent method to minimize the discrepancy between them. The overall algorithm is shown on the right. However, this method has two drawbacks. First, there will be some information loss during the conversion. The loss cannot be zero. Second, the exponential turn in the loss function will make the optimization challenging to converge. On the other hand, we present a closed-form solution for this equation as shown on the left, where W is the discrete Fourier transform matrix. The overall algorithm is shown on the right. Here we show how to derive the closed-form solution. We first add a variable b equal to 0 to both sides of the equation, yielding the first equation. Expanding this equation into matrix form, we have the second equation. Now, by setting h equal to n-1, we have the third equation. At this point, V is a Vandermonde matrix. Although the Vandermonde linear system is unstable in general due to numerical precision issues, if the lambda k are pairwise distinct, the equation will have a solution. By selecting the lambda, the above equation can be reformed as below. By comparing the first row, we have. However, the coefficients from TNN are not guaranteed to satisfy this equation. To ensure that this equation is satisfied, we introduce another variable, which we call an inclusive equation reformulation process. Therefore, we have. Based on the above equation, we can determine the coefficients b using the expression. Here on the left, we compare the time overhead and the relative error of our proposed closed-form solution ETSC and gradient-based method. It can be observed that ETSC exhibits significantly lower time overhead compared to the gradient-based methods, while having much smaller errors. On the right, we show the impact of hyperparameters on inference time in memory. Compared with the original TNN implementation and cache implementation, our method have much lower time and memory cost. Here, we evaluate the extrapolation capability of the converted model using ETSC. It can be observed that our model exhibits extrapolation ability similar to TNN. Moreover, for the hidden states of 768 and 1024, ETSC achieves average perplexity comparable to TNN. We also conduct experiments on other long conva methods to assess the performance of ETSC. We trained an SG-Conva language model and applied ETSC to convert the Toeplitz representation to SSM representation. As shown, ETSC achieves similar extrapolation ability to SG-Conva, with even lower average perplexity values. Thanks.